This lecture is entitled Observational Study Designs. This is Part 1, Introduction and Learning Objectives. Hello, my name is Dr. Jacina McGregor. I'm faculty in the College of Pharmacy, located up on the Portland campus at OHSU. This lecture covers observational study designs and the concepts of causality and association. There are two primary learning objectives for this lecture series. The first is to distinguish between the concepts of causality and association. Specifically, you should be able to understand what the hierarchy of study designs are as they relate to determining causality. You should also, after this lecture, have familiarity with Bradford Hill's criteria for establishing causation. The second objective is to identify and describe distinguishing features, limitations, and most appropriate clinical research role of primary observational study designs. Those would be the case report, case series, cross-sectional, case control, and cohort studies. Following the lecture, you should be able to identify how each study contributes to causal inference, and identify what are the common advantages and disadvantages of each design. You should be able to identify study designs based on key features, and you should have familiarity with the terminology, including being able to identify research questions, exposures and treatments, outcomes and diseases when reviewing a study. This is Observational Study Designs, Part 2, Causation and Association. As we move through this lecture, we'll be using an example with the medication azithromycin. Azithromycin is a macrolide antibiotic, commonly used for bacterial respiratory infections and for some sexually transmitted infections. It's been in use in the United States since the mid-1980s, and in 2010 it was the most prescribed antibiotic in outpatients in the United States. However, there are some concerns that have arisen more recently about potential adverse effects. This is because other macrolides have been associated with increased risks of sudden cardiac deaths, perhaps mitigated through an increased incidence of ventricular arrhythmias. So the research question that we'll consider as we move through discussions of study designs, causation, and association will be, is azithromycin use associated with an increased risk of death due to cardiovascular causes? So to frame this question a little bit more, let's focus in on part of the question. Specifically the part that says, is azithromycin use associated with an increased risk? What does it mean to be associated with an increased risk? Well, first let's consider the difference between association and causation. When we conduct studies, we can measure association. We cannot measure causation. Associations are a statistical measure of the dependence or relationship between two events, characteristics, or variables. We measure associations in samples. We use statistical tests and modeling to make inferences about the population through statistics. So what do we mean when we talk about causal inference? Well, causal inference is based upon a body of research and knowledge. Observations made in a research study provide us with evidence for making causal inferences. So we need to determine the degree to which the data that we observe supports or refutes whatever causal inference we're trying to make. There's not really any one set of rules or guides for how we weigh evidence to support or refute causation. However, there have been proposed guidelines or proposed criteria in the past that we can turn to help us as we think about how we weigh the body of evidence and whether an association is truly because of causation. Those include Koch's postulates, which you learned in microbiology courses that you took before pharmacy school, and it includes Bradford Hill's criteria for causation, which we'll discuss more today. This table presents Bradford Hill's criteria for causation. Each of the criteria are listed on the left-hand column. The middle column provides a definition or description of what that criteria presents. And then the right-hand column provides some critique as to the positives or negatives regarding that criterion. So let's consider each of them. The first criterion is the strength of association. So as I mentioned, we can measure associations. And as we move into the next lecture, we'll talk more specifically about what kind of measurements we use, specifically risk ratios, odds ratios, etc. But those measurements have a magnitude to them. The larger they are, the more likely that it is that the association we're observing is causal. And that's because it's difficult to find an alternate explanation for that causation. For that association. We'll talk more about alternate explanations for associations that we observe, but it is still possible that even a large association can be explained away by other reasons. And so strength of association is not a requirement for causation. However, it can provide us with evidence. The second criteria is consistency. And that is meant by consistency of observing the same association across different studies, populations, etc. This is helpful when we perform meta-analyses. Those are studies that summarize the results of multiple other studies. However, differences in study designs, threats to the validity of the study, and other reasons can cause lacks or inconsistent results. Another criterion is specificity. And that's the specificity between the exposure and the treatment and the outcome that you're interested in. That exposure treatment can be isolated and shown to produce a specific outcome independent of other factors. It's thought to provide more evidence towards causation. However, in medicine, causes that are neither necessary nor sufficient are the most common. A single exposure can often lead to multiple outcomes, and so this scenario is rare. The next criterion is temporality. This is the only criterion that is required for causality. That is to say that the exposure or the treatment or the drug has to occur before the disease, before the outcome of interest. If that temporality is not present, causality cannot be present. The next criterion is biological gradient. This is the dose-response relationship. And while often we observe this relationship and it can be strong evidence for causation, there are threshold phenomena and nonlinear associations that are true too. So the absence of this effect does not necessarily preclude causation. The next criterion is biological plausibility. That is to say that the association fits well with our previous existing knowledge of physiology. However, this can be subjective. Similarly, the next criterion is coherence, and that is to say that the association fits with known related mechanisms of disease. And this can also be subjective and is related to what we know about other related mechanisms of disease. The next criterion is experimental evidence. In humans, the primary example of this would be randomized control trials. However, this is not data that are always available. Finally, the last criterion is analogy. That is to say that similar mechanisms for disease causation are known. This is similar to coherency and biologic plausibility, and again, can be somewhat subjective. So again, while these criterion are helpful in allowing us to assess the presence of causality, only temporality is required for causation. So when we think about causal inferences, we need to think about what are the possible explanations for any observed data or association that we have from a study. Well, first, the first possibility is that what we're observing is the truth. It's a true and causal effect. The next possibility is that what we're observing is due to chance. Well, how do we rule that out as a possibility? That's where we use statistical tests to identify what the likelihood is that the observations that we have are due to chance versus not. The next two possible explanations are confounding and effect modification. This requires us to consider the study design that was used, the statistics that were used, and to make a subjective assessment to determine whether these two factors are actually the true alternate explanation for what we're observing. And we'll talk about that more in subsequent lectures. Similarly, bias is another possible explanation for observing an association in a study. And again, we have to evaluate the study design and make a subjective assessment as to what we think the effect of the bias could be on the observations that we have. So in our process of making causal inference, we have to evaluate single studies as well as the body of evidence to determine what the likelihood is that the observations that we have are due to the truth or the causal effect versus these other alternate possible explanations. This is actually how we assess a study's internal validity. Similarly, when we think about the different study designs, there's a hierarchy for making causal inference from these designs. Part of this is because of their ability to establish high internal validity, meaning a high likelihood that alternate explanations are not present for what we observe. And the study design's ability to establish temporality, the only requirement for causality, is a large part of the structure of this hierarchy. So you'll see on the hierarchy that the randomized clinical trial is at the top, meaning that it provides us, generally speaking, with the most evidence for making causal inference, followed by cohort studies, case control studies, cross-sectional studies, and case series. However, the hierarchy is only a guideline. It is not an absolute. It's based upon each study's design's ability to establish temporal relationships between cause and effect, and the ability to rule out alternate explanations. Yet the quality of the study is still important. In reality, a good cohort study can be better than a poorly conducted randomized control trial at providing us evidence towards causality. Therefore, critical appraisal of the studies are necessary. So let's go back to thinking about our research question. Is azithromycin use associated with increased risk of death due to cardiovascular causes? Well, we've discussed what association causation refers to. And we're going to talk more about risk and measuring association in subsequent lectures, but just to foreshadow a little bit, let's think about what is risk. Risk is the possibility that something bad or unpleasant, such as an injury or loss, will happen. The probability that an event will occur, for example, that an individual will become sick or die within a stated period of time or by a certain age. In clinical research, it's a term for measures of the probability of a given outcome. So as we move forward, we'll be talking more about measures such as incidence, cumulative incidence, and incidence rate. Risk measures quantify probability of a given outcome in a group of people. In contrast, measures of association compare risk between groups of people. You can also compare proxy measures of risk. But we need to measure association to provide evidence for causal inference. Measuring risk alone does not provide us evidence for a causal inference. We have to be able to make comparisons. This is Observational Study Designs, Part 3, Case Series, Cross-Sectional, and Case Control Studies. If you recall, we discussed the hierarchy for causal inference in regards to which study designs contribute more evidence towards making causal inferences. We're going to talk more now about the observational study designs that are of primary interest to us. When I just talk about observational study designs, as you can see from this branching tree that classifies studies. Observational studies are those in which the investigator did not assign which patients or which persons got the exposure or treatment of interest. Further, we're specifically interested in those studies in which individual level data are collected. We'll talk about 4 different study designs, 2 of which are considered primarily to be descriptive studies. Those would be the case series and cross-sectional studies. And 2 are considered analytical study designs because they include comparison groups and have some temporal component involved in the design. Those would be the case control or cohort studies. So again, we'll talk about these study designs in the context of a research question. Is azithromycin use associated with an increased risk of death due to cardiovascular causes? So how do we answer this question? Well, first, what is the exposure of interest? In this question, the exposure of interest is azithromycin use. What is the outcome of interest? For this question, the outcome of interest is death due to cardiovascular causes. Keep this in mind as we talk about how we would design a study to answer this research question for each of the designs that we talk about. Moving forward, I'm going to be using some new notation that I want to explain. First, the letter E will be used to refer to exposure. The exposure could be a drug, or some chemical, or some treatment, or medical procedure. In figures that I draw, I will designate people that have been exposed as a purple stick figure. The letter D will be used to designate the disease or the outcome of interest. And in figures that I draw, a red X over a person will designate that someone has experienced that disease or outcome. The letter E with a bar over it will be used to designate people who do not have the exposure. And in figures, that will be represented by a black stick figure. And similarly, the letter D with a bar over it will be used to designate persons without the disease or outcome of interest. And in figures, that will simply be any individual without the red X present over it. So if we think about our example, again, our exposure of interest is azithromycin use, and our disease of interest is cardiovascular death. So a purple stick figure would represent anybody who has used azithromycin but did not experience cardiovascular death. A black stick figure would represent a person who has not used azithromycin and did not experience cardiovascular death. A purple stick figure with a red X over it would represent a person who has used azithromycin and did experience cardiovascular death. And a person that is a black stick figure with a red X over it would represent a person who has not used azithromycin and did experience cardiovascular death. So we're going to start by talking about the case series study design, which, as you recall, was at the bottom of the causal inference hierarchy, meaning that it provides the least degree of evidence towards making causal inference. So what is this study design? It is a study of only, quote, case patients, meaning there is no control group or comparator group involved in the study design. And you can use it to describe the exposures that occur among those case patients. Now, the study name is still the same even if we use it to study or describe persons who were all received a given drug instead of all the people who had the same outcome. In that case, it would be a study of exposed patients only, where you would describe the outcomes that those exposed patients experienced. So let's think about this example of case series, specifically with our azithromycin research question. So an example of how you could do a case series with this research question could be if an emergency department physician observes a series of patients who experience cardiovascular death after coming to the ED. They could go back and look at what medications were prescribed to the patients at their preceding ED visit. So as you can see from the figure, all 8 patients experienced cardiovascular death. 6 of the 8 were exposed. They're purple, meaning that they had azithromycin prescribed at their preceding ED visit, whereas 2 of the patients did not. So what are the advantages and disadvantages of this design? Well, generally, it's done as a convenience sample, for example, like a series of patients seen by a healthcare provider, and it's very useful for hypothesis generation. However, you cannot measure association and really cannot make any causal inference. There's no comparison group. We can't say anything about the patients who did not experience cardiovascular death. Even among patients who did not experience cardiovascular death, the exposure of azithromycin is likely very common. We don't know that it's any more common among those who died than it is among those who did not die. So now let's consider the cross-sectional study, one step up on that hierarchy of study designs. To conduct a cross-sectional study, you first identify the population of interest. Then you define a point or period in time that you're interested in. You take a sample and identify who is exposed and who is diseased, and then you can calculate the burden of disease in that sample. So again, thinking about our azithromycin research question, how would we apply the study design? We could look at all of the organ death certificates for this year. We could identify persons with cardiovascular death, and then call their families to identify if the deceased was taking azithromycin at the time of their death. And then we could calculate the burden of disease. So what kinds of measures are possible? Well, again, there's no temporal component here. We don't know too much about how far in advance they had started taking the azithromycin before they experienced cardiovascular death. We don't know if the azithromycin use preceded any of the cardiovascular symptomology that was linked to their cardiovascular death. It's hard to establish if the drug really was part of the causal pathway for that cardiovascular death. However, we can talk about the burden of disease. We can talk about how much cardiovascular death occurred in this sample, and that thus might be representative of the population. And we can talk about how much azithromycin use occurred in the people who died due to cardiovascular causes versus those who did not. While we can make some comparisons, we're making comparisons about the burden of disease. We cannot make any statements about risk. And that'll become more apparent as we talk about higher level study designs. So what are the advantages and disadvantages of this cross-sectional study? Cross-sectional studies are generally low cost, relatively fast. They're good for assessing prevalence. Prevalence is a measure of the burden of disease that we'll talk about in future lectures. And they're very good for hypothesis generation, for thinking about what could be going on causally that we might want to test in further higher order study designs. A disadvantage is that there's no time component. Again, you'll remember that temporality is the only required component of causality. So we cannot assess if the exposure actually preceded the disease process. And typically we're collecting information only from a single point or a short duration of time. Next, we're going to talk about the case control study. To conduct a case control study, we first look within the population of interest. Then we start by sampling disease and non-diseased persons, meaning people with and without the outcome. Then we look retrospectively, meaning back in time, and identify what their exposure status was. So again, we sample people who have the disease, who do not have the disease, and we look backwards in time. You'll see the arrow is going in reverse to identify which of those people were exposed and which were not exposed. So it's thinking about our azithromycin example again. We could look among state Medicaid beneficiaries in a database that covers 2000 to 2010. We could sample people who had cardiovascular death, who we'll refer to as our cases, and for each one of them we could sample 3 people who did not experience cardiovascular death, a control. So you'll note here that typically to do a case control study, we often sample the controls in some set ratio to the case patients. Then we look back in time to see who had claims for an azithromycin in the past week. Thus, we identify among the cases and the controls who had azithromycin exposure. Then, we can measure association. While we're looking back in time, this study design does include a component of temporality, and we can measure association within case control studies. As we'll discuss in future lectures, not all measures of association can be calculated with this design. However, association still can be measured. So what are the advantages and disadvantages? Case control studies are always retrospective. Thus, there's no follow-up, and it's typically less expensive to conduct than a prospective study. It's good for studying rare diseases or rare outcomes because the sampling strategy is based upon identifying people with and without the outcome. And you can study multiple exposures because as you identify people with and without the outcome and go back in time to look at what their exposures were, say using medical records or claims data, you can identify multiple exposures to study at one time. But the disadvantages are that case control studies often rely on existing data. And existing data often means that sometimes the data you want are missing or misclassified. You cannot calculate incidence or risk. And as we talk more about what incidence and risk are and how we calculate them, that'll become more apparent in future lectures. Because of this, though, it's more difficult to establish the time relationship between the exposure and the disease outcome. And we have to really think more about the data source that we're using to think about how valid our temporality assumptions are between the relationship between our exposure and our disease outcome.